Do you want to change it or?
We're going to swap over the.
Okay, fine. Just.
This is your laptop?
Yes.
Okay.
So.
Just need the.
Oh, come on. This one. It's the laptop. I don't know why. So that's one. And that's the other one.
How you doing?
It's okay. It's not okay.
That's very red.
My speaker knows it's not.
Yeah. Ah. Nice. Right.
1 second. I just need to try.
Oh, this is going to be fun. Right. Up there.
Somewhere here.
Yeah. And then your pocket or can go on your belt or something. Yeah, that looks good. Resolution okay?
I don't think so.
Okay, so maybe
1 second.
maybe 1024 by 760.
Exactly.
Yeah, 60 hertz.
This one?
Yeah, that should be fine.
Okay. No.
Mirror display. Okay, so that would be nice.
Okay. It's okay, yes.
Right.
Ready.
Right, thank you very much. Okay, Pavel.
Okay, so my name is Paweł Jakub Dawidek. I came here from Poland to talk about GEOM. Any FreeBSD users maybe around? Okay, nice to meet you guys. Okay, sorry about a bit tiny, shiny presentation, but I was playing with Keynote recently, so. Okay. Okay, so I want to talk about GEOM. This is the way FreeBSD handles storage. What does it mean? Or maybe. Let's start from what GEOM is not. So, GEOM is not a file system. I know that you Open Solaris guys like file systems a lot, but GEOM is not a file system. GEOM is also not a device driver or pseudo-device driver. And GEOM is also not a logical volume manager. So maybe you wonder what kind of storage GEOM actually handle. So GEOM basically is a framework. It's there to provide infrastructure to, for implementing IO request transformations. It's also responsible for handling auto-discovery of storage media, for example. It also provides management interface, so userland tools can communicate with GEOM framework to configure stuff. And also, which is most important, GEOM cleans up a huge mess we had before. And I think Open Solaris still has similar mess. But let me talk more about GEOM, so maybe you will be able to compare. Okay, so this is the case where there is no GEOM. So if you want to access like this device from userland, you just communicate with defFS. And if file system want to use a disk or a partition, it also has to talk to defFS. And defFS talk to device drivers. And in case of GEOM, userland tools still talk to defFS, and defFS talk to GEOM, but file systems can use GEOM directly. And GEOM actually talks to device drivers. Okay, so what kind of data structures we have in GEOM? So we have a class. Class basically implements a transformation. Every kind of transformation is separate GEOM class. For example, partitioning is separate GEOM class. RAID 1 implementation is a separate GEOM class. Stuff like encryption, compression. GEOM, using clover letters, is an instance of a class. So for example, a GEOM in GEOM terminology is, for example, mirror of two disks. We also have providers. Provider is basically a disk offered by GEOM. You can access this disk using /dev entry. So in FreeBSD, actually every disk-like device is provided by GEOM. It's basically GEOM provider. And we also have consumers. Consumers are used to communicate between classes. So consumer basically connects another GEOM class to particular provider from yet another GEOM class. This way, for example, our mirror device can talk to disk providers from different class. Okay. So once again, a class implements a transformation. Class has a name. It also defines paste method. It's used by GEOM to tell the class that some new provider appears. So class, for example, can paste for its own metadata. We have destroy GEOM method. When basically GEOM provider disappears, GEOM will call destroy GEOM on this class. And we can initialize and finalize class on load and unload. And examples of GEOM class are, for example, disk. Disk is just a GEOM class in FreeBSD. It communicates with disk drivers. But stuff like MBR, which provides partitioning, it's also yet another GEOM class. RAID 1, just an example of GEOM class, nothing more. So, GEOM. GEOM is a very virtual thing. It doesn't appear anywhere. It just allows to group objects better. For example, not for example, but GEOM also has a name, so it can be found easily. It defines few methods like start. This way, GEOM sends IO requests to a particular GEOM. It has access method. When consumer wants to connect to provider, GEOM will call access method, and we can deny or accept access. There is orphan method, which is called, but I will talk about this later because it might be a bit complex. There is spoiled method. It's called when provider is open for the first time for writing. And there is dumpconf, which basically dumps configuration. Also, as you can see here, there are some GEOMs which can have providers and consumers, but also there are GEOMs that have only consumers or only providers. There could be also, of course, GEOM which has no providers and no consumers, but there is no much sense on doing that. Sorry, one click too much. Okay. Come on. Sorry, I will just try again. Okay. Okay, so provider. As I said, it's disk-like device offered by GEOM. It has a name. Those are basically three most important properties. Provider has a name, so you can access GEOM provider through /dev entry. It has size. It's basically disk size, and also it has sector size. 512 bytes for regular disks. It also has access counts. Access counts are used to know if provider is open for reading, is open for writing, or if we have exclusive access to the provider. And we have consumer. Consumer has no name, but it basically connects one GEOM class with another GEOM class. So when I create consumer, I want to connect this consumer to another GEOM class. For example, mirror class, write1 class, creates consumers to connect to disk providers from another GEOM class. It also points at provider it has opened, because consumer can be attached only to one provider. But attaching consumer to provider is not enough. You have to open provider to gain access. Okay, so GEOM by design is modular and extensible. What does it mean? We can load classes, GEOM classes at any time. So for example, we can load disk class, and disk providers will appear. We can also load mirror class, which will auto-discover disks and configure mirror provider. When we load partition class will discover that mirror has two partitions and will just create new GEOM providers. And we can also load, for example, encryption class, which will deploy encryption on one of the partitions, for example. GEOM is also freely stackable. This means that we can mix the classes in any order we want. In this particular case, if we have two disks, we can. It's basically it doesn't matter for GEOM. The order doesn't matter for GEOM at all. So we can mirror two row disks and partition mirror provider, or we can partition disks and put encryption only on one half of the mirror, and mirror one encrypted provider and one partition not encrypted. It may not make sense in this particular case, but if you imagine a situation where disk 1 comes from the network, or sorry, disk 0 comes from the network, you may want to encrypt one half of the mirror, which is accessed through the network, and local disk you may leave unencrypted, for example. So the idea is that FreeBSD provides tools, not policies. We basically are not here to tell you how you should do your work. We just want to provide tools so you can do your work best you can. We just want to help. So we don't, GEOM doesn't, this is quite a problem with, I think, most of volume managers, logical volume managers, where you have strict ordering. You cannot mix the things in any order you want. ZFS is also such an example, but ZFS is quite special. There is actually logic in there not to be able to, for example, put mirror on stripes, not stripes on mirrors, for example. But basically, GEOM allows you to choose your order of operation. Okay, I would like to talk a bit about special GEOM classes. So, first of all, there are no special GEOM classes. GEOM is there to protect that every single GEOM class has exactly the same rights. There are no special class which has some more rights than the other. You can do whatever you want. This is basically also this also gives you opportunity to stack your classes as in any order you want, because there are no interactions between classes that one class depends on another class. So every GEOM class is treated exactly the same. Also, every GEOM provider is treated exactly the same. So you can, for example, put file system on raw disk, or you can put file system on partition, you can put file system on mirror, encrypted provider, wherever you want. It doesn't matter for GEOM. And basically, any sort of transformation is legal. You can implement your own transformation, just load your kernel module, and it will just work. You don't have to modify GEOM, you don't have to modify other GEOM classes. Okay, how auto-discovery in GEOM works? It's called GEOM tasting. So let's say we have a class disk which has two GEOM providers, disk 0 and disk 1. And we load mirror class. What happens? GEOM will call mirror's taste method, saying, hey, this is maybe when you load a class, you will be given all existing providers for tasting. So in case of mirror class, GEOM will give mirror a chance to taste or read metadata of any GEOM provider available in the system. So when we load mirror class, GEOM will say, hey, this is disk 0, you should look at it, for example. Mirror creates new GEOM, for example, creates new consumer, discovers metadata attached to disk 0 provider, and gains access to this provider. So we have three kinds of access: read, write, and exclusive. Read, of course, is easy, but in case of write, we cannot open provider for writing if it's already open exclusively. And we also cannot open provider exclusively if it's already open for writing. So GEOM gives mirror a chance to taste another disk, disk 1 in this case. And mirror creates another consumer, connects, attaches to this disk 1 provider, also asks for access, and creates, based on those two disks, its own GEOM provider, mirror 0 in this case. And once mirror creates new provider, all the other GEOM classes are also informed that new provider arrived, so they can taste metadata of this particular provider. For example, if this mirror provider have some partitions configured, MBR class will be called. See, this is mirror 0 provider. Maybe you can have metadata there, and MBR class can create its own providers on top of the mirror. And in this case, some other class will be called for tasting. It will attach to mirror 0 provider, and it will open it for reading, for example. So this is how tasting in GEOM works. Now, let's see how access counts work. So as I said, we have 3 access counts: read, write, and exclusive. I will tell a bit more. Basically, if you want to read data from provider, you have to open it for reading. If you want to write data, you have to open it for writing. And if you don't want others to interrupt you, you should open it exclusively. Let's assume we have configuration like this. As a side note, maybe I will tell you what def class is. Basically, GEOM itself doesn't talk to defs. GEOM itself doesn't present GEOM providers in /def directory. There is a def class which tastes all the GEOM providers and creates devices which can be accessed from, for example, userland. So it's not really a GEOM who creates those defs entries. It's more def class responsibility. Okay, so if def class, for example, some user application opens provider for reading, it will go down to the disk. So as you can see, if you are not familiar with FreeBSD, we have 2 partitioning systems. We have MBR, which is basically master boot record partitioning system, which is what is used in any other operating system. But FreeBSD also has this BSD label partitioning. And regular partitions, as you know them, we call slices. And partitions are created by BSD class. So we have disk. We have two slices on this disk, and we have 2 partitions on slice 1. And if partition A is open for reading, it will go down to the disk, and all the providers will be open. For example, another application tries to open partition B for read and write. For example, let it be some B partition is most of the time used for swap. And it can be opened because BSD class knows that those 2 partitions, A and B, don't overlap. So there will be no problem at opening partition B for writing. It will not interrupt this userland application reading A partition. It will also goes down to disk 0. Now userland application wants to open slice number 2, and it is also permitted because slices 1 and 2 don't overlap. But imagine a situation when userland application wants to open disk itself, for example, for writing. It cannot because it's already open exclusively. So GEOM will deny access to this provider. Okay. Okay. This is how GEOM handle disk removal. It will be a bit long, but if you want, you will understand how it works exactly. So let's say that disk 0 disappears. someone plugs cable, unplugs cable or whatever. What happens is that this class calls orphan function on this provider. This tells GEOM to inform other GEOM classes that this disk won't be able to operate anymore. So all the GEOM, all the disk 0 consumers will be notified about that. Then dev class will call GEOM will call dev class orphan method. So this way GEOM tells dev class that disk 0 is not longer there. Also, GEOM calls MBR's class orphan method. So basically, idle consumers can self-destruct. This consumer is only attached, but it's not open. So it will basically detach and self-destruct. Okay, now MBR class orphans its own providers because those two slices are based on disk 0. So once disk 0 disappears, those two slices have to disappear as well. So MBR class calls orphan function on disk 0 S2. Again, consumers get notified. GEOM will call orphan method of dev class. Dev leaves disk 0 S2. It's open, so it has to first close access to disk 0 S2. We detach and destroy consumer. Okay, now disk 0 S2 has no consumers attached, so basically GEOM can garbage collect it. Okay, so slice 1 left. MBR calls orphan function on slice 1. Dev class is informed. It detaches because it's not even open. It destroys consumer. Okay, so it's not the right description, but basically BSD class is this should be BSD. Orphan method is called on slice 1. BSD orphan its own providers. Partition A, dev class is informed. It closes access to this provider, detaches and destroys its consumer. GEOM can garbage collect a partition. Then another provider is orphaned, dev class is informed, close access, detaches and destructs its consumer. Okay, now we can clean up, finally. So we detach from slice 1, destroy consumer. Okay. Okay, this was a bit boring, but it's not the last animation, I am afraid. Okay, so
just one little question about the
sure.
the functioning of that orphaning procedure and presumably applicable to other parts. Where a sorry, I get the terminology here. Where a class has, say, multiple providers,
Mm-hmm.
and it's going through and orphaning all of these in order to deal. Is there some defined order that does these in, or is that just purely by chance?
No, it basically goes from bottom to the top, because if disk disappears, it's class responsibility to inform GEOM that disk provider won't be longer available. So
Yes, but for instance, where you had the MBR class had the two slices,
mm-hmm.
You called the orphan method on its second slice first. The BSD class had two partitions. You called the orphan method on its first
No.
within that one class, or is it?
I called orphan first on a second slice only to make animation more clear, because if you would go first on orphaning BSD class, you will be probably forgot about this slice too. But there is no particular order. It's class responsibility to choose the order, for example. Yes.
So, looking at the way that, and also related to the origin functionality, when you take, for example, a mirror, right? It's pretty clear that no matter what's using that mirror above it, removing one half of that mirror is probably safe. Removing that second half of the mirror, it seems like you would want to have some way to veto the operation, because, for example, you should actually process them on it or something. Is there some sort of veto capability or
basically, in case of a mirror, because there is a question if one half of a mirror disappears, what happens? Or
I was using the mirror as an example, right? One half of the mirror would be fine, but there are cases where you definitely don't want to lose a component in your storage stack, right? Because, for example, your processes might depend on this component. There may be other things that depend on it that are equally important to your database, for example. It seems like my experience is with Solaris. In Solaris, we have this facility called RCM that allows you to interpose and basically reject a hot plug operation if it would be considered unsafe.
Okay.
If there's something like that.
So basically, I will stick to this mirror case. So once you lose one half of a mirror, it's fine. And basically, mirror class won't destroy its own provider. It will be informed that one of the half is not available anymore, but it will be still functioning fine. It won't orphan its own provider, because there is still another half working. In case you lose second half, there is not much you can do actually, and in this case, it's of course GEOM class has to decide what it has to do with its own provider, but basically it will orphan its own provider, and if there is file system attached, there is another GEOM class called VFS, which connects file systems to GEOM providers. And file system itself can decide what it wants to do with this orphan event. It can unmount forcibly file system, for example, or it can hang all IOs until provider reappears. It's basically class decides what to do about this event. So in case of file systems, if you don't want to lose this particular file system and you don't want to forcibly unmount it, you can basically hang all further IOs, future IOs, and wait for all those providers to reappear, for example, reconfigure your mirror and start to handling all those queued IOs.
It's not as if the software has an opportunity to veto the human pulling a cable out.
Yes,
The
exactly.
software can't stop the human from pulling the cable.
Yeah.
That's right. We can only.
We can work on it.
To be clear, I wasn't imagining a cable pull. I'm imagining before the unit pulls the cable, right? I mean, those of us who have unfortunately had this experience with Windows, where with USB media, you're supposed to unmount it, detach it, make it safe, right, to remove. With Solaris, you use config ADM, and config ADM can go and basically call into these providers to ask, is it safe? Is this in a situation where it's safe for me to remove it?
This is actually this is very easy, because you can only check access counts. If provider is open, you veto or you advise not to remove the disk because it's open. So you can look at the access count for this. Okay, so we have another operation which is a bit similar to orphaning. It's called spoiling. It is how GEOM handles metadata updates. For example, you have a disk 0 again, and you have two slices on this disk. But some userland application, for example, we decide to overwrite this metadata. So we call the BSD label utility, which will basically overwrite MBR metadata with BSD label metadata. So the userland application opens disk for writing, and once disk is open for writing for the first time, GEOM sends spoil event to this class. It basically says, look out, this provider you are attached to was open for writing, so its metadata can be updated from outside. And what this class should do, it basically detaches from this disk and destroys its own slices. Those slices are not open. The class is only attached to this disk. It destroys consumer and it destroys providers. So MBR class, it's no longer attached. And BSD label writes its own metadata. And once it's close write access, and GEOM sees that write access count went to 0, it will give this disk for tasting to those classes. So GEOM will give this disk 0 for tasting to MBR class. This way MBR class can say, oh, my metadata wasn't actually changed, so I can create partitions again. But in this case, those metadata were overwritten, so MBR finds nothing interesting at this point. But also another class, BSD, it's called, and BSD class discovers its metadata. So it can configure consumer and creates whatever BSD label written. In this case, it creates 2 new partitions. If one of those slices you've seen before would be open for writing and open exclusively, we couldn't call this BSD label command because it will be denied to open disk 0 for writing. So GEOM protects about overwriting metadata silently, or any data silently, actually. Okay.
Quick question for you.
Sure.
So essentially what you're saying there is that if you indecently touch one of those drives in a mirror, the entire thing will just throw it out and just present it to you as a simple disk or whatever outside the mirror, isn't it?
No, actually, mirror class, once you remove one half of a mirror...
No, if you actually touch one of the disks in the mirror class, all that propagates up into the mirror class and then it'll throw it out because it's being touched outside the mirror.
If you touch metadata, if you overwrite metadata? Or, yeah. Yes, but in case of mirror class I implemented, even if mirror provider is not open, it still holds its own components open for writing and exclusively. So you cannot still overwrite metadata this way. But in this case you are talking about, yes, this would be the case. If you clear mirror's metadata, mirror won't rediscover its metadata, so it won't recreate its provider. So it will be gone. But it's not the case in real world in this implementation of write one we have in FreeBSD now.
All right, well, the second part of the question was if that's the case, and if you do the same thing to the other drive, the other half of the mirror, what's left, what happens? But since it's not a realistic case, then...
Yeah, but basically it's quite rare to have providers not open. If you plug in new disk and you don't have file system on it or whatever, it's closed. There is no access count, so you can edit metadata and put whatever you want. But once you mount file system, it will be open, so you won't be able to overwrite metadata. Oh my God. Okay, so IO requests are represented by struct bio. Basically, those structures are not transitive, so every class have to clone the biostructure and pass that down. Of course, you don't clone all the data, only this small structure. You have two functions to send a request down. GIO request takes consumer as argument and this biostructure, so you know which consumer you want to use to send IO down. Okay, we have 5 IO requests. So read and write are quite, should be self-explanatory. Delete is used, it depends on the class, how it's implement delete. For example, if you have class which handles flash devices and you want to implement wear leveling, this is the request you want to use. If for example, encryption class sees this request, it may want to override the data with some random stuff. It depends on the class how it is implemented. Most of the class just ignore the requests, but some of them can do something useful. There is BioFlash, which basically sends requests to disk drive, for example, to flash the cache. And you can also ask for some attributes. Okay, there are quite a few existing GEOM classes just to prove that GEOM was a good way to go. We have plenty of stuff implemented on top of GEOM. Any kind of transformation is implemented using GEOM framework. So as you can see, those are quite basic functionalities which live as separate GEOM classes. You can mix them as ever and in any order you want. But there are quite more actually. And the last case is quite interesting for you Open Solaris guys. In FreeBSD implementation, ZFS also has to access disk or partitions as GEOM providers. So in case of FreeBSD, there are two GEOM classes, VDEF, which basically allows ZFS to open disk partitions or whatever and operate on them. And in case of FreeBSD, there is no difference if you put one disk, one encrypted disk, one mirror, and put write Z, for example, on top of those all using ZFS. You can use any GEOM provider with ZFS. And also, this is at the bottom, VDEF class is at the bottom. At the top, you want to also, ZFS has can export its storage as ZVol. It's also in FreeBSD, it's just GEOM provider. So it's just another GEOM class which provides its data through GEOM providers. How does it look in a picture again? So when we have 3 disks and we have ZFS, at the bottom we have VDEF ZFS class, which operates on consumers only. This class doesn't create any providers. It's just there to be able, for ZFS to be able to connect with other GEOM providers. So we can attach those consumers to those 3 disks, for example, in write Z configuration. And at the top, we have ZFS vol class, which operates only on providers. So it doesn't use consumers because it doesn't connect to anything. It just provides storage to, I don't know, userland applications, to other file systems, to other GEOM classes. And other classes can connect to those providers. Okay, that would be all. Any questions? Do we have time for questions?
One question. You had that thing with half of the mirror was direct access to the disk and the other one was encryption somewhere else.
That's right.
What's the speed of that such a?
Was it speed?
Yeah, what's the speed? What's the speed of a ride for such a contraption?
It depends, of course, on your hardware. But
I think the question Presumably.
Yes, of course, in such configuration, encryption probably would be the bottleneck, but
And it doesn't lie to you, say, yeah, I wrote that, so don't worry about it.
yes, exactly. But it depends. If your file system can do some asynchronous operations, it will just work in the background, for example. But of course, it depends on the implementation. So in this case, probably it will be a limiting factor. It's not good to, for example, encrypt two providers, two half of the mirror separately, and create mirror on top of that, because you pay a price basically multiple times, as many components you have in your mirror. But it's better to just encrypt mirror provider once. That's right. Yes.
Sorry, we'll have to take other questions later in the gas bagging session at the end of the day.
Okay.
Thank you very much, Pavel. It's
Thank
great
you.
to have you here. And of course, here I am trying to get everything on time, and my next speaker has just run out of the room. Where'd you go?
Maybe it's a good time for a break.
Right. Well, amongst yourselves, or take another question. Right? No, we're just scheduled for questions. Hang on. There you go. Bow's on top.
Thank you. Thank you.
Is there any way to override that to say that this particular class always should be handled by that system?
Okay. My mistake. It is actually time for a break, so let's get a coffee.
Thank you, James.
Not all the classes.
This is my job, right? Run around, get things
Yeah,
organised
that's right.
for you when you're...
So we've got 15 minutes before the next speaker.
It won't be good to say that only this class stays in this particular provider.
Or these
Well,
notepads around?
Sometimes it might be if you have some very slow provider like
I don't know.
you don't want every
Not those.